Assalamualaikum and good day everyone. We are group AS1205D and today we will be presenting on valence bond theory or VBT. Valence bond theory is one of fundamental theories in chemistry that explains how atoms form covalent bond. According to this theory, a covalent bond is formed when the atomic orbitals of two atoms overlap, allowing them to share a pair of electrons. The theory was first proposed by Walter Hilter and Fritz London in 1927 and was later expanded by Linus Pauling, who introduced the concept of hybridization to better explain molecular structure. Valence bond theory is important because it helps us understand chemical bonding, molecular geometry, and the strength of covalent bond. Now, let's move on to the objective of our presentation.
Hi, before we begin, let me briefly explain the objective of our presentation. Okay, first, to understand the basic principles of valence bond theory, which explain how covalent bonds are formed through the overlap of atomic orbitals. Second, to explain orbital overlap, band formation and hybridization, including sigma bonds, pi bonds, and the different types of hybridization such as sp, sp2, and sp3. Finally, to discuss the applications and limitations of valence bond theory in explaining molecular structures and properties. By the end of this presentation, we hope everyone will have a better understanding of how valence bond theories helps us explain chemical bonding in molecules.
Hello and Assalamualaikum. My name is Nurul Nadra binti Muhammad Zamri and my student ID is 2024-959-795. As for the basic principle of valence bond theory, the valence bond theory states that a covalent bond forms when individual atomic orbitals overlaps, localizing a pair of shared electrons between two specific atoms. As these atoms approach one another, the attraction between each atom's electron and the opposite nucleus increases until they reach an optimal minimum distance, and at this point, the potential energy is minimized, creating a stable chemical bond that dictates the molecule's geometrical shape.
Good day everyone, my name is Nur Shakira Shahmina binti Nur Amali. My student ID is 2024539225 and I will be explaining orbital overlap, sigma bond and pi bond in valence bond theory. Let's begin with orbital overlap. According to a valence bond theory, a covalent bond is formed when the atomic orbital of two atoms overlap. During this overlap, each atom contributes one unpaired electrons with opposite spins. These electrons are then shared between the two atoms, forming a stable covalent bond. The extent of orbital overlap is very important because it determines the strength of the bond. In general, the greater the overlaps between the orbital, the stronger and more stable the covalent bond will be. There are two main types of orbital overlap. First, head-on overlap, which forms a sigma bond, and second, a side-by-side overlap, which forms a pi bond. Now, let's look at the sigma bond, which is represented by the symbol sigma. A sigma bond is formed through an end-to-end or head-on overlap of atomic orbital. This overlap can occur between two s orbital, an s orbital and a p orbital, or two p orbital. As you can see from the slide, there were a diagram of each overlap. Because the orbital overlap directly along the line connecting the two nuclei, sigma bond have the greatest orbital overlap. As a result, they are the strongest type of covalent bond. Another important characteristic is that a sigma bond is always the first bond formed between two atoms. It also allows free rotation around the bond axis because the electron density is distributed symmetrically around the bond. For example, like I show in the slide, in methane or CH4, all four carbon-hydrogen bonds are a sigma bond. Next is the pi bond, represented by the symbol pi. Unlike sigma bonds, a pi bond is formed through side-by-side overlap of two parallel p orbitals like I showed in the slide. Since this type of overlap is less effective than head-on overlap, pi bonds are generally weaker than sigma bond. A pi bond cannot exist by itself. It is always formed after a sigma bond has already been established. Another characteristic is that pi bond restricts rotation around the bonds because rotating the atoms will break the sideway overlap between p orbital. For example, that I show inside the slide, in 18 or C2H2, the triple bond between the two carbon atoms consists of one sigma bond and two pi bond. To summarize, orbital overlap is the basic concept behind valence bond theory. Head-on overlap forms strong sigma bond, while side-by-side overlap forms weaker pi bond. Understanding these two types of bonds help us explain the strength, stability, and bonding behavior of covalent molecules.
The next one is the hybridization. Hybridization is a key part of valence bond theory. It happens when an atom mathematically makes its own outer orbitals, which have similar energies but different shapes, to create a brand new set of identical orbitals known as the hybrid atomic orbitals, and these new paths are perfectly aligned to form strong chemical bond. As for the first hybridization, which is the sp, the first thing first is you have to draw the Lewis structure. When you draw the Lewis structure, you will know how many sigma bonds are there. If there is a sigma bond, you have to make sure that the electron is partially filled, just like in the photo. If it have a lone pair, then you need the full fill orbitals. However, in this case, we only have a partially filled orbitals because we only have two sigma bond. Thus, after filling the 2s, you will do a promotion. Why promotion? Because there is no lone pair. So it means that you do not need the full orbital, and instead you have to have two half-filled orbitals. And then you do a hybridization, and we will call it as sp, because one half-filled orbital SS and one half-filled orbital sp. This is why we will combine it, hybridize it to become sp. As for the second one, which is the hybridization for sp2. So first you have to know how many sigma bond is there. As for the BRCl3, they have 3 sigma bond. So you have to know that you have to have 3 half-filled orbital and no full-filled orbital because there is no lone pair. So when you do the basic filling, you will fill about 3 of them because due to the boron valence electron, which is 3. So when you do a promotion, you have to know that the two things that I say, the bond, the sigma bond and the lone pair, there is no lone pair and 3 sigma bond. Thus you have to separate the full fill orbital. And after the promotion, you will do the hybridization, and in the hybridization you will combine the S and the P house together and become sp2. Last but not least is the sp3. As for the sp3, we are focusing more on the C, which means that the C and H4 has 4 sigma bonds and no lone pair. So that's why in the first stage you have to fill out based on the carbon valence electron, which is 4. So when you fill it out, and then you will do a promotion. So the promotion, you have to keep in mind about the sigma bond and the lone pair. As we all know that there is 4 sigma bond and no lone pair, meaning that you have to have 4 half-filled orbitals. That's why in the picture there is only 4 half-filled orbital and no full-filled orbital. As for the hybridization, you have to combine both houses, so it will become sp3 because in S house there is 1, and in P house it has 3 half-filled orbital.
Good day everyone, I'm Miss Maya Binti Hamdi and my student ID is 2023462842. Now, I will present the applications of valence bond theory. Okay, firstly, valence bond theory explains how covalent bonds are formed. Okay, a covalent bond is produced when two half-filled atomic orbitals overlap and share a pair of electrons. Greater orbital overlap results in a stronger and more stable bond. Secondly, the theory predicts molecular geometry through hybridization. For example, methane has sp3 hybridization, which gives it a tetrahedral geometry, while boron trifluoride has sp2 hybridization, resulting in a trigonal planar geometry. Okay, lastly, valence bond theory helps predict molecular properties. Molecular shape and bonding influence properties such as polarity, bond angles, and chemical behavior. Therefore, the theory helps us understand why different molecules have different physical and chemical properties. Although valence bond theory is useful, it has several limitations. Okay, firstly, it cannot explain the paramagnetic behavior of oxygen molecules. Experimental studies show that oxygen contains two unpaired electrons, whereas valence bond theory predicts that all electrons are paired. Secondly, the theory assumes that electrons are localized between two bonded atoms. Therefore, it cannot accurately describe electron delocalization in molecules such as benzene. Finally, for molecules with more complex bonding, molecular orbital theory provides a more complex explanation of electronic structure and molecular properties. Okay, so in conclusion, valence bond theory is a fundamental theory for understanding covalent bonding. It explains bond formation through orbital overlap and uses hybridization to predict molecular geometry. In addition, it provides a basis for understanding molecular structure and properties. Although it has limitations, particularly in explaining paramagnetism and electron delocalization, it remains an essential concept in chemistry and is complemented by molecular orbital theory. Okay, so I think I'm gonna stop here. So that's all from me and my team. Thank you so much and hope you guys enjoy our explanation about valence bond theory. Bye bye.